So chapter 16 is going to be about thermodynamics, and this is going to expand upon and use a lot of ideas that we talked about in General Chemistry 1. So before we dive too deep into that, I do want to make sure we're all at least on the same page of what kind of topics you should theoretically know or be comfortable with, and kind of make sure we're all aware of what those are before we dive too deep into applying them. So we're going to talk about heat and enthalpy are the big things we want to be comfortable with. So thermodynamics is all about energy. We are generally focused on thermochemistry, energy, and chemical systems. And specifically, moving forward, we're going to be looking at energy involved in actual chemical reactions. That could be energy produced as, say, heat in a chemical reaction, say like you burn fire. It could be cold associated with chemical reactions. Say, also not just heat, but say ordered motion. You burn gasoline, that's a chemical reaction to get your car to move forward, right? That is directed motion. That is all still energy being harnessed from a chemical system and turned into some sort of mechanical motion. Generally, when we are talking about thermochemical kind of studies, we're usually interested in something that we're going to call the system. So this would be something that we're looking or kind of focused on. That's usually going to be a chemical reaction for us. And in fact, for us, it's just going to be a chemical reaction moving forward. There are cases we've talked about in General Chemistry 1 where it's maybe a liquid or a solid that's not changing in that way. But everything else is the surroundings. So, you'd have, say, a chemical reaction in a solution. So the solvent and the beaker and the air are the surroundings. There, we're going to be looking at, say, the flow of energy between those things. If a chemical reaction gives off energy, it goes into the liquid, it goes into the beaker, it goes into the air, warms up that stuff. And that sort of transfer of energy as heat is the thermal energy transfer. Our symbol for heat is going to be a lowercase q. Sometimes you'll see an uppercase q. That generally actually means something different. Also, it gets confusing with, say, reaction quotients. So lowercase q, I always stick to for heat. And so the thermal energy corresponds to the motion of molecules. And one of the things we want to always remember is that temperature corresponds to average motion. So higher temperatures mean the molecules are moving more. So if you have an object that is at a high temperature, its molecules are moving, say, a lot. So this ball, say, hot, so these lines represent motion. So these molecules are moving a lot. What literally happens then is they will literally collide with the, say, solvent molecules or the surrounding, say, liquid molecules. They will literally collide and make those liquid molecules start to move. That will hit other molecules and make them all start to move more. And so that would lead to heat flowing into the liquid because the liquid molecules start to move more. They have more thermal energy. They would go to a higher temperature. The molecules that were initially hot have cooled down. They have less overall motion, so heat will flow from hot to cold until all molecules have the same average motion. They're all at the same temperature. When heat flows like this, we can see there's kind of these opposite perspective, the idea of heat leaving the system or the heat going, say, into the surroundings, right? And so this into or out of, but it's the exact same amount of heat. The only thing that different is the perspective, and that is reflected with a negative sign. So heat leaving a system would be the negative of the heat going into the surroundings. So enthalpy is then H, is our symbol for that. That'd be total heat content. We've talked about enthalpy quite a bit throughout the course, talking about exothermic, endothermic, like phase changes and things like that. For Le Chatelier's principle, those ideas. And so generally that's always been concerned with delta H. We very rarely, never talk about absolute enthalpy. It's always delta H. And the reason for that is that delta H for a constant pressure change corresponds to the heat associated with a change. The reason why we use it in chemistry is because chemistry is occurring at constant pressure, right? When you're doing a reaction in, say, a beaker in the lab, it's under the atmosphere, right? The pressure of the atmosphere is the pressure that's exerted on that reaction. That's a constant value. And so the heat of reactions is really characterized by the delta H of the molecules in that reaction. So the delta H of the, say, molecules going from reactants to products will tell you what the heat will be for that reaction. And the sign convention that we use, we've talked about this, we've seen before, that exothermic reactions release heat and delta H will be negative. Endothermic reactions take in heat and delta H will be positive. In this case, the reaction is always the system, and the solvent or air or whatever you're doing the reaction in is always going to be the surroundings. And so heat in is always positive, heat out is always negative. So if we know delta H for a reaction, we can figure out the heat associated with the reaction of any amount of reactant or product, right? And so knowing delta H is a really valuable tool. And so one of the things that we do that it really helps us with that is the fact that delta H is a state function. What that means is the change in enthalpy between two different states, in this case, basically mixtures of reactants and products, doesn't depend on how we make those changes, kind of but in just the endpoints. So basically the delta H, the enthalpy change of going from, say, carbon and oxygen directly to carbon dioxide, would be the same as if we did it in, say, a two-step process, where first we create carbon monoxide and then the carbon monoxide becomes carbon dioxide. Right, so this idea that state functions don't depend on how you make the change, just what the overall change is. So you get like a small delta H plus another small delta H, and those combine exactly to give you the big delta H. With that in mind, we can calculate what are called formation enthalpies. These are symbolized delta HF. This is the enthalpy of forming a compound from its elements. So you'll note that things that are elements have a delta HF of 0 because there is no, basically, they are the elements, so there's no reaction there. But something else, these are generally negative. We can see things like that. So, HF has, negative 271 kilojoules per mole is released if you form it from its elements. So, we get these kind of nice measurements, and these can be tabulated for, you can just find huge tables, sapling is a massive one, for any sort of compound you want, what the enthalpy of formation is. What we can do is use these enthalpy of formation to think about reaction enthalpies. Again, all about state functions. So say I'm interested in the change in enthalpy of going from dimethyl ether to ethanol. Okay, so that would be one reaction step. I can instead reconceive of that as, well, what happens if dimethyl ether becomes its elements, right? It goes backwards, undoes the formation enthalpy, and then those elements rearrange into ethanol. And the reason why we would think about it in that way is because these delta HFs are tabulated values. So we could look up what those numbers are, do some subtraction, and figure out what the delta H of the reaction I'm interested in is, right? We can get a number for that reaction that we're actually interested in. And so that's a really useful tool that lets me make predictions about delta H for any reaction with these tabulated delta HFs. And so that's super powerful. And so the enthalpy change for any reaction can be predicted. Delta H of reaction is just the sum over the delta H's of all the products. You're basically forming those from their elements minus delta HF of the reactants. You are undoing those from their reactants, right? This delta HF value assumed you're forming those reactants, so you're undoing them. That's why there's a negative sign in front. And so you just look up those tabulated values and you can figure out the delta H for any reaction, which you can then use to figure out the heat for any reaction, amount of reactant you're using, which is very, very useful. So why do we care about thermodynamics is a good question. And one, we want to be able to effectively apply and use heat, something like, I want to be able to cool a piece of metal. I want to heat my house. How much heating oil should I burn? Those are really important questions that we want to be able to answer. kind of higher level in terms of for looking at this kind of stuff. We can also make predictions without doing experiments. We can do things like Hess's law, we can use formation enthalpies. And really what we can do is we can get delta H for a reaction. We can be able to predict the heat for a reaction, the heat associated with a reaction, based on reference data. Based on reference data for other reactions or about compounds. We don't need to be, say, doing a bunch of experiments to make predictions. And that's really one of the big goals of thermodynamics, of how can I use these physics interactions, these physics relationships of heat and energy to avoid having to do chemical experiments and make predictions about experiments before I do them. You know, I want to know if a reaction is going to be like super exothermic. I want to know that before I say run the reaction, so that way I can say run it like an ice bath. Something I don't, you know, I can be mindful that it's going to get hot, and that can be sort of very useful and important.
Okay, welcome to chapter 16. We're looking for questions on participation 324. It's going to be due Tuesday, March 24th. Again, this first set of videos we cover in the week 10, midweek 10 homework, acid-base titration lab. If you're not liking chapter 16 or 17, don't worry. We got another acid-base lab to do, pre-lab technique and notebook. I want to get those set up by 11 a.m. on Wednesday. If you have any questions about anything, let me know. Otherwise, welcome to week 10, chapter 16. We're just going to start plenty of videos in this set. See you in the next one.